This is a short video on intermolecular forces. There are three main types of intermolecular forces, and these intermolecular forces are what hold one molecule with another molecule. So in other words, one covalently bonded compound to another covalently bonded compound. You can kind of think about it as being glue. Those three main intermolecular forces are dipole-dipole, the other one's called hydrogen bonding, and lastly, we have London dispersion forces. In dipole-dipole, these only happen in polar molecules. So if you want to know if something has dipole-dipole forces, it has to be a polar molecule. Now, we talked about polar molecules back a couple chapters ago when we drew the Lewis dot structures, and then we had to look at the shape to figure out if they were polar or nonpolar. Now, if they're polar, that means they're going to have oppositely charged ends because there's a large difference in the electronegativities. So if we look here, this is one atom, and we can see there's a negative on one side and a positive on the other, so it's oppositely charged ends. And then over here, same thing with this one and this one. So they've all kind of arranged themselves so that the negatives and the positives attract. So it means between these two different ones, we have this force of attraction, and that would be the dipole-dipole force. Now we can also see that it's occurring over here anytime that we have oppositely charged ends of molecules. So for example, if we were going to look at a compound, let's say water, has a bent structure, and between those two, oxygen has a higher electronegativity than hydrogen, which means the electrons are pulled more toward this oxygen. So in this case, this end of the molecule is kind of negative because all the electrons are being pulled that way, and this end would be positive. So that means if I were to have another water molecule, it would also have this same negative and positive. There would be an attraction between the negatively charged end of one and the positively charged end of another. I could look at another example. Let's say if I had something like SO4. In this case, O and S, there's a small difference in electronegativity, but because all of the electrons are being pulled out evenly, then this molecule would be nonpolar. And because it's nonpolar, it would not have dipole-dipole. So no dipole-dipole forces. This one, because I had the oppositely charged ends, this one would have dipole-dipole. I could also look at something like maybe HCl. In this case, Cl likes the electrons more than H because it has a larger electronegativity. So the electrons are pulled toward the chlorine. So I have a negative on this end and a positive on this end. That means if I have another HCl nearby, it also has the negative and the positive. So there would be this force of attraction, this dipole force, between those two oppositely charged ends. So this one would also have dipole-dipole forces. So that's the first kind. Our second kind of intermolecular force is what are called hydrogen bonds. Now these aren't actually bonds, this is still another force of attraction, and it occurs anytime that you have hydrogen attracted to a highly electronegative atom like nitrogen, oxygen, or fluorine. Now there's two criteria. Obviously, if it's hydrogen bonding, you have to have a hydrogen atom, but that hydrogen atom also has to be bonded to an O, N, or F in the molecule. So in the case of HF here, we can see that H is bonded to F, and there's a force of attraction between the hydrogen on one atom and the fluorine on another one. So here's one molecule. This would be my other molecule. So I have a force of attraction between the hydrogen on one molecule and the fluorine on the other one. In the case of water, here's like a water that I had drawn earlier. So I do have hydrogens, and I do have it bonded to an O. So here's one water molecule. Here I can see that I have another water molecule, and there's this force of attraction between the oxygen on one molecule and the hydrogen on the other one, and that's what those dotted lines represent. So if I had something like we'll say ethanol. In this case, I do have a hydrogen and I do have it bonded to an oxygen. So that means if I had another one of those same ethanol molecules, I would have this force of attraction between the hydrogen on one and the oxygen on another one. Now, if I were to have a slightly different structure, where I have this, in this case, I have hydrogens, but they are not bonded to the O. So this would not have hydrogen bonding. So that's the second kind, hydrogen bonding. The third kind are the easiest, and these are dispersion forces. Everything has a dispersion force. So you don't have to worry about what kind of a molecule it is. If it has hydrogen bonding, if it doesn't, or anything else, everything has dispersion forces. Now they're usually only important if they don't have the other two forces, because those other two forces, the hydrogen bonding and the dipole-dipole, those are stronger. And so nonpolar molecules will exhibit this induced dipole. So what happens is I have one molecule that ends up with a dipole. It's going to cause another molecule then to set up a dipole. So here they both are nonpolar. This one has a dipole that occurs just by the movement of the electrons. That causes a neighboring molecule to also have a dipole. That's why it's called an induced dipole. And because this end is positive and this end is negative, I'll have this little bit of attraction between those two oppositely charged ends. This is the weakest force, though, because as soon as those electrons move, that dipole will be gone and be destroyed, and therefore that force will no longer exist. So it's very short-lived and for that reason very weak. And in terms of our forces, the strength, we have dipole-dipole as being the strongest, and hydrogen bonding, and sometimes hydrogen bonding can be just as strong, if not stronger, than dipole-dipole. But the weak then are these dispersion forces. Those would be the weakest. And in terms of when we look at molecules and boiling points, these intermolecular forces can have a distinct difference on the boiling point, or an effect on that boiling point. If we have very strong forces, that means it's going to have a higher boiling point or a higher melting point. So when we look at a series of compounds, if we can identify what kind of forces they have, then we can say something about the boiling point. So if, for example, it had dipole-dipole and hydrogen bonding, like the case of water, it has both, that means it has two kinds of glue that hold those molecules together. And in order for it to boil, those molecules are going to have to spread apart and start to turn into a gas. And they're not going to want to do that if they have really strong forces. So that means that the boiling point on water would be higher than something like, let's see, we'll look at something in the same column. So here's our water. Sulfur is in the same column as oxygen. But this case, H2S, I'm not going to have hydrogen bonding because I don't have an O, an N, or an F that the H is attached to. So because this one has the two kinds of glue, the dipole-dipole and the hydrogen bonding, this one only has the dipole-dipole. That means out of these two molecules, this one would have a higher boiling point. So by looking at what kind of forces that we have, we can tell a lot about the properties of that molecule. So that is a short video talking about intermolecular forces.